So we will continue our discussion on the joint probability density function. Joint probability density function. Okay, so it is usually expressed as fxy of xy. Okay, you can actually compare this with this with your joint probability function. That means joint probability of A and B, and you know that how to find this. The joint probability of A and B is usually given as the probability of A given B into probability of B. The same notion you can use here. Okay, that means it is nothing but fx given y of x given y into f of y. That's it. Okay, so this is the joint density formula. Anyway, we can also have also another formula. This is the case actually in the case of if the events are dependent events. Okay, it's a general formula anyway, general formula which can be used for dependent events. Okay, dependent events. Okay, but you have seen that if two events are independent, if two events are independent, then the occurrence of one will not affect other. That means the probability of A given B, that means whatever it may happen, that means if B has occurred or not, it doesn't matter on the probability of A. That means it is nothing but the probability of A, because this B will not have any influence because they are independent, because B will not influence. Okay, so this formula we have already seen in the probability theory, so we can use the same notion here also. If the events are independent, if the random variables x and y are independent, then fxy of xy is nothing but fx of x multiplied with fy of y. Okay, that means you can see here, if the events are independent, you have already seen that the probability of A comma B is nothing but the probability of A multiplied with probability of B. Okay, it is because probability of A given B is nothing but the probability of A, as I have explained here. Okay, it is due to the independence of the events. So we have a new formula also. Okay, this is the case of independent events. So if the events are independent, the joint density function is nothing but the product of individual density functions. Okay, now we will see a problem. It is given, let x and y are independent. It is given that sorry, not independent, x and y are x and y be two jointly continuous random variables. Okay, and the density function is given, the joint density is given, it is given as x plus c into y square. Okay, and this is for the limit x is between 0 and 1, and y is also between 0 and 1, and it is equal to 0 otherwise. Okay, so this is the density function. So the first part of the question is to find the constant c. Okay, and the second part of the question is to find the probability that x takes the value between 0 and 1 by 2 and y takes the value between 1 by 2 and 0. That means the joint probability that we have to find. So we have to find a joint probability. That means x and y is between actually 0 and 1 by 2. Okay, that is the question. So we will solve this problem, and you know that to find the first part of the question, to obtain c, we know that if you have a joint density function, if you integrate this over all possible values of x and all possible values of y over the entire range of x and range of y, okay, then dx dy, actually if you integrate the complete probability density function, you will get 1, okay, as in the case of one dimensional random variable. So we will use this notion to obtain the value of c. So it is nothing but you have the range for x. The range for x has been given. You know that the range for x and range for y, okay. So we will integrate over x and y, and what is our function? It is nothing but x plus cy square, okay. And first we will integrate with respect to x, so the x is changing from 0 to 1, and then we will integrate with respect to y, and the y is changing from 0 to 1, and this integral will be equal to 1, okay. So 1 is equal to integral 0 to 1 x plus cy square dx dy, okay. So we will find this integration. So 1 is equal to, okay, so if you integrate x, you will get half x square, okay, then plus c into y square is a constant now, and you will integrate with respect to x, so c into y square into x. Now you have this variable, and this is for y. Again you have to integrate with respect to y, but x changed from x is equal to 0 to x is equal to 1. So you have to use this notion, okay. Now you can see here, after substituting this, you will get 1 is equal to, actually if you put x is equal to 1, then this become 1 by 2 plus c into y square, okay. Next you have to integrate this value 0 to 1. So you just substitute, you will obtain this, and you have to integrate with respect to y, okay. Now you will get it as, if you integrate with respect to y, this half become half y plus c into y cube by 3, okay. Next you have to put the limit for y from 0 to 1. Then you will get, if you put 0 anyway, it will become 0, but if you put 1, you know that it will become half plus c by 3, okay. That's it. This is equal to 1. So you can take this guy here. So 1 minus 1 by 2 is equal to c by 3. That means 1 by 2 is equal to c by 3. That means c equal to 3 by 2, okay. This is how to obtain the value of c. So I hope this is clear to you. So we got the value of c as 3 by 2. So our fxy now become, it is nothing but x square plus c is 3 by 2 into y square, okay, and this is equal to 0. This is for the value of x between 0 and 1, and y is also between 0 and 1, okay. So this is otherwise. So this is what the density function. Now the second part of the question, we will see the second part of the question. The second part of the question is to find this probability. You have to find this probability. So the probability that x takes the value between 0 and 1 by 2 and y takes the value between 0 and 1 by 2 is nothing but, you have to just integrate the PDF, the joint PDF x and y, and x varying from 0 to 1 by 2 and y varies from 0 to 1 by 2. So if you integrate this, I am going to skip some steps, you can verify. You will get it as 1 by 3 by 4, okay. If you integrate this, you will get, this is 3 by 32, okay. So that is the answer. So this is how we can find this. This is a simple integration. You can use the same procedure as we have used in part A, okay. So but you have to just substitute the value of c, okay. Now you can see here, this is how to obtain the probability by using the joint density function, okay. Now we will see a new topic which is known as the random process. This is very, very important topic, random processes. Okay, random processes. So you know that if you conduct a random experiment, you have a sample space, you have a random experiment. Suppose each event is denoted by zeta. Okay, this is an event. Okay, now if you map this event into a real line, this is a real line to a real number. Okay, let's say it is a x. So for each event you have an x. It is nothing but this x we will call, usually we will call this x as a random variable, and x is the value of random variable, right? Value of random variable. So we have seen the notion of random variable. Now corresponding to, so this is the notion of random variable anyway. Now we are talking about the random process. Okay, so now we are talking about the random process. In a random process, for each outcome, actually for you have a random experiment, each outcome we are assigning a function of time. Okay, we are assigning a function of time x of t. So this is nothing but a random process. Okay, so in general the random process, this is a particular sample function. Okay, this is a sample function of random process, sample function of random process. So in general we will be representing the random process as x of t and zeta. This is the usual representation of a random process. So a random process is nothing but a function of time. Actually it is a function of time. It is a function of time. A random variable is not a function of time. Actually a random variable is nothing but a value. You can see here it is a value x, or a capital X in general, and x. So a random variable, actually sorry, a random variable is just a value, but a random process is nothing but a function. So it is a function of time. Basically it is a function of time. So usually it is represented by x of t comma zeta. To avoid this confusion, you have seen here this random variable is also usually represented by x of zeta, but we will be using only a notation that is x. Similarly, instead of this x of t comma zeta, we will be generally using x of t. So x of t is a random process. So we have two types of random process. One is nothing but a discrete, the continuous time random process, and another one is the discrete time random process. Okay, and the another one is the discrete time random process. Okay, so we have two things. So a discrete continuous time is usually represented as x of t. Okay, a discrete time is usually represented as x of n. So you can assume like this. So x of t is a random process, x of t of zeta 1 anyway, for example, or x of t comma zeta in general. Okay, so x of t comma zeta 1 means it is a random process corresponding to the event zeta 1. Okay, so this is a random process. You see here the signal is, it is a signal. You can see here it is a signal and it is a function of time. Okay, so this is a realization of a random process. Suppose we have another realization of the random process, x of zeta 2 is another realization of the random process, maybe like this something. Okay, this is a random process. So this is a function of time. Okay, it's a random process. So if you consider a particular instant, let's say it's t1, the value is nothing but x of t1 of zeta 1. Okay, similarly if you are considering same thing, if you are considering t1, then x of t1 comma zeta 2. So you can see here all these are actually some values, right? this is also a value, this is a value again. Okay, so all these are nothing but the random variable. Okay, so at a particular time instant, actually you have a random variable. So this, you can see that this random process is a function of time, and it is actually contains the random variables. Okay, it is actually a set of random variables, okay, which is arranged as a function of time. So that is nothing but the continuous time random process. So you have different examples anyway that I will give you. A discrete time random process you can represent like this. You have a discrete time random process x of n and zeta 1. You have some samples like this. So this is a discrete time random process, that is, it is discrete in time. So it is n, index is n equal to 0, 1, 2, 3, 4, 5, 6. Okay, now if you are considering a particular n, that is x of, here n is equal to 4. Okay, so x of 4 comma zeta 1 is nothing but a random variable anyway. Okay, this is a random variable. And now we have another realization as explained here. So you can have something like this is a random process which is x of n comma zeta 2, which is corresponding to the event 2. Okay, so which is a function of discrete time. So this is n equal to 0, 1, 2, 3, 4, 5, 6. Okay, so these are all the, for example, for n equal to 3, you have x of 3 comma zeta 2. Okay, so this is nothing but a random variable. Okay, so this is nothing but the random variable. So n is discrete, actually this is a discrete. Okay, here t is continuous. Okay, that's how we have two types of random processes. So it is nothing but a collection of random variables. I think this is clear to you. So I will give you some examples for the continuous time random process. So continuous random process, this is nothing but continuous. And we have some examples for discrete time random process, discrete random process. So this is showing discrete. Okay, so we have continuous and discrete random process. So you have a random process x of t comma zeta, which is nothing but zeta into cosine of 2 pi t, where with your zeta is a random variable, which is, it is a random variable, is a random variable. Well, zeta is a random variable which is uniformly distributed in the interval. It's a uniformly distributed in the interval -1 to 1. Okay, so this is the random process you can see here. So it is a function of time. That means you can see here, this is showing, this is actually showing the amplitude, right? Amplitude of the process. So you can see here, you can have a realization x of t comma zeta 1. For example, it takes some zeta 1. So the peak amplitude, sorry, this is a cosine wave, sorry for this. So we have a cosine wave with amplitude, this is zeta 1. Okay, now another realization of the same thing, zeta 2, you have something like this. Okay, let's say zeta 1 is equal to 1. Let's say this is zeta 1 is equal to 0.5. So this is how we have different realization. So according to the different values of zeta, you have different processes. Okay, so you have a set of processes, and you can see that the zeta is a discrete random variable. Now we will see another example. So this is an example for the continuous random process, and another an example for the discrete time random process is x of n comma zeta is equal to some bn, where bn is a random number, random binary number. Okay, binary number. That means you have a process something like x of n comma zeta 1. For example, one realization may be like 0, 1, 2, sorry, not 2, because it can be our 0 binary number. That's why it's 0, 1, 1 like this. Okay. Or it can be another realization like this, zeta 1, zeta 2 is nothing but you can have 1, 1, 1, 0 like this. Okay. So this is another realization. So this is nothing but a discrete random process. Okay. Now we will see another example for a continuous random process. A continuous random process. We will see another example for this continuous random process. Another example as y of t comma zeta is equal to cosine of 2 pi plus zeta. Okay, with zeta is a random variable in which is uniformly distributed in minus pi to pi. So this is showing the uniform distribution. Okay, uniform distribution. So you can see here it will be something like this, y of t comma zeta. Okay, and you have something, suppose zeta is equal to 0. Suppose zeta equal to 0, there is no phase shift. That means this is showing the phase of the signal. So the phase is a random variable. That's what this example is showing. So previous example was showing actually the amplitude is a random variable. Okay, now the phase is a random variable. It can be anything. Now you see here, if the phase shift is equal to 0, you will get the signal like this. Okay, if you have another thing, if so this is if zeta is equal to pi by 2, so you will be getting is equal to pi by 2. So you will be getting something like this. You see here the amplitude is same. So this is zeta is equal to pi by 2. Okay, and the first one is actually this is with zeta equal to 0. So you have different combination, many infinite number of waves are possible by using this, because you have infinite number of values between minus pi to pi for the value of zeta. So this is how the random process will be looking like. Suppose if you are considering a time instant, let's say this is time instant t1, the value of the random variable here it is x of zeta which is equal to 0, and sorry, it is nothing but x of t1 with zeta equal to 0. Okay, this is a random variable basically. And if you consider another part, for example, at the same time you have something here, this is nothing but x of t1, but you have a zeta which is equal to pi by 2. Again, this is another random variable. So everything is nothing but a random variable at a particular time. So if you are observing at a particular time instant, it is nothing but a random variable. This is known as the continuous random process. I hope this part is very clear to you. Okay. Now we will see some of the important properties of this random processes. Okay. Now I am going to another topic. That is the joint distribution of time sample. Okay. So the joint distribution is nothing but, you know what is joint distribution, we have already explained in the previous lecture. So joint distribution is used to characterize the random processes. Okay, whether it is continuous or discrete, whatever it may be, we will be usually using the joint distribution for characterizing the random processes. Okay, so we have a main thing. Suppose you have a random process which is something like this. Okay, something like this, and this is a function of time. Okay, let's say this is a x of t is a random process. I am just purposefully omitting the zeta, okay, to have simplicity in the notation. Now let us consider the time instance. Let's say this is t1, this is t2, this is t3, t4, t5, okay, etc. like this. So you can consider the time instance like this. Now the joint cumulative distribution is defined as, first of all I will define the joint cumulative, you know what is cumulative distribution. Joint cumulative distribution is defined as, you know, I told you at each time instant it is nothing but it is showing a random variable x1, and at time instant t2 it is showing x2, at time instant t3 it is showing x3, at time instant t4 it is showing x4. So all these are nothing but the random variables, right? All these are nothing but the random variables, and so on. This is how it is, and this is here x5, okay. All these are random variables, and so on, okay, and so on. So the joint distribution for the random variable x1, x2, x3 in general up to xk, which takes the value, that means each random variable takes the value small x1, takes the value small x2, this takes the value, this takes the value small x3, this is x3 is here, right, x3, and this takes the value x4, and this takes the value x5. That means like this, and so on, and so on, okay. That means it takes the value, x1 takes the value, the capital X1 takes the value small x1, okay, like this. X2 takes the value small x2, x3, etc. up to xk is nothing but, you know, this is the probability that x of t1, that means this is a random process, and x of t1 is nothing but the value of the random process, at time t1, okay, which takes the value less than or equal to x1, because we are talking about the cumulative distribution function. Then x of t2 takes the value less than or equal to x2, okay, and x of t3 takes the value less than or equal to x3, and so on. X of tk takes the value less than or equal to xk. This is nothing but the joint distribution. So the joint distribution definition is almost same as in the previous case that we have discussed in the random variable, but you can see this is x of t1, x of t2, x of t3, that's the difference, okay. So it takes the value, that means this value at particular time t1, it takes the value which is less than or equal to x1. So that is the joint density, and the corresponding PDF we can define the PDF also. The PDF also defined as, the joint PDF can be defined as f of x1, x2, etc. up to xk, x1, x2, x3, etc. up to xk is nothing but, so this is how it is nothing but the PDF of the corresponding PDF. This is nothing but the corresponding PDF, okay, corresponding PDF, okay, or joint PDF we can say in general, joint PDF. So similarly for the discrete random process, also we can use the same notation. So this is actually useful for the continuous random process and the discrete random process, okay. This notion is same for discrete and continuous, because we are talking about the cumulative distribution function. Now for the discrete random process, the joint PDF, the joint PMF we can say is nothing but the probability, that is P of x1, x2 up to xk, which takes the value x1, x2, x3 up to xk, is nothing but the probability that x of t1 takes the value equal to x1, comma x of t2 takes the value equal to x2 and so on, x of tk takes the value which is equal to xk. This is same thing as you have studied in the probability theory that regarding the random variables. Okay, almost the same, but only notion, only difference is just you have x of t1 here and this is a x of t2 here, x of tk here. That's the only difference. Okay, now we will see an example. Okay, we have a random sequence. We have a random sequence. Whenever we are talking about a sequence, it is nothing but a discrete random variable. Am I correct? Because we are talking about a sequence. If we are talking about a continuous time function, it is a continuous random variable. Okay, so it is a random sequence. Let's say there is a random sequence xn, and this random sequence is having it is having a Bernoulli random variable. That means with Bernoulli random variables with probability which is equal to half. What is a Bernoulli random variable? That means you have only two outcomes, either yes or no, or head or tail, like this. Okay, that means you have either 1 or 0, for example. Okay, then the joint PMF, actually we are not talking about PMF because this is a discrete random variable, because it's a discrete random variable. So we are talking about discrete, not random variable, actually random process, discrete random process. So we will talk about PMF. What is that PMF? The PMF is nothing but the probability that x1 takes the value, okay, small x1. Similarly, x2 takes the value, small x2. Okay, x2 and so on. This is x of t1. I have made a mistake here. Actually, it is not t1, t2. We can say this is n equal to 1 in this case. This is n equal to 2, like this. Okay, this is n equal to nk, some value. Okay, like this. So we can also represent this guy, actually these things, as x of n1, n equal to 1 is as x1. Okay, and x of n equal to 2 is as x2. Okay, like this. So the probability that x1 takes the value x1, x2 takes the value x2, and so on. Okay, xk takes the value small xk. So this is nothing but the joint density. This is the joint probability mass function. But you know that each trials are independent. You know that each trial, that means if you are tossing a coin, if you are tossing coin 2 times, then each trial number 1 and 2 both are independent. And each trials, you see here, each trial is independent, and we can expect only 2 outcomes. So the joint probability is nothing but, you have the joint probability that x1 takes the value x1 multiplied with probability that x2 takes the value x2, and so on, multiplied with probability that xk takes the value xk. So this is nothing but, this probability has been given, this is p, this is also p. Okay, and this has been given, and this p has been given as 1 by 2. So this is 1 by 2. Okay, multiplied with 1 by 2, multiplied like this, 1 by 2. This is nothing but 1 by 2 whole raised to k. So this is how you can find the joint PMF for this particular process. Okay, now we will see another example. We will see another example of a continuous process. So let us see here, we have a noisy signal, filtered noisy signal, or noisy signal in general. Another example of a DC signal with noise. Okay, this is an example, DC signal with noise. That means you have a DC signal which is A and it is corrupted with a noise. That means a noise has been added to it. Okay, let's say this is W of Wi is showing the noise signal at the ith instant. Okay, now you measure this signal at different time instant and you are getting xi. Okay, and this is your value. Now in general, this is how the random the value of the random variable look likes, and in general you can say that xi is nothing but a plus the noise signal wi. Okay, this is the generic notation anyway, but this is actually talking about the values. Okay, and this is talking about the random process, a continuous random process. Okay, this is the value of the random process. Okay, now what is the joint PMF of this? And it is given that each Wi is independent. It is given that each Wi is independent. Then we can actually consider, then we can find the joint PDF of this. The joint PDF is nothing but f of x1, x2, etc. up to xk or xn in general, x1, x2, etc. up to xn. This is nothing but the joint PDF can be given as, since everything is independent, I have already told you if the events are independent, the joint density will be just the product. So if it fx of x1 multiplied with fx2 of x2 multiplied with like this, okay, and fxn of xn. Okay, so this is how you can find the joint PDF. Okay, now if x1, x2 up to xn are having same PDF, which is a Gaussian distribution, then we can basically write like this. We can basically Gaussian distribution, and which is in general we can say fx of x is 1 by 2 pi sigma square root of this and e power minus of x, okay, square by 2 sigma square. Okay, now we can write like this. If everything is Gaussian, and if the mean of x1 is equal to mu x1 and mean of, in general I can say if mean of xi is mu xi, then if all are same, then which is equal to mu x, then I can write something like this. My joint PDF fx1, x2, x3 up to xk, which takes the value x1, x2, x3 up to x, I think it is xn anyway. This is equal to fx I, because each one, everything is equal, fxi of xi, we have to multiply n number of times, I is equal to 1 to n. That means this is a product instead of summation. Actually this is a product because we are actually multiplication. Okay, this is showing multiplication. So if you multiply this, you will get, you have the term, actually this term is 1 by root 2 pi. What is this square root? Square root means something raised to 1 by 2. So if you are multiplying n number of times, then it will become 1 by 2 pi sigma square. Okay, sigma square. If everything is having same mean and variance, okay, same variance, sigma square or sigma x square, then I can write like this. I can write like this, sigma x square whole raised to 1 by 2. Since I am multiplying n number of times, then it become n by 2. Okay, then e power, and you know that e power one term is xi minus mu x by 2 sigma x square. Okay, and if you are multiplying, and this is minus, if you are multiplying n number of times, the exponential term will be added, because e power a multiplied with e power b is nothing but e power a plus b. So it will be added. So I have a summation on the top, and this summation varies from I equal to 1 to n. So my joint PDF fx1 x2 up to xn will take the form 1 by 2 pi sigma x square whole power n by 2 into e power minus of summation I equal to 1 to capital N xi minus, sorry, I have made a mistake here actually, xi minus mu x the whole square divided by 2 sigma x the square. Okay, this is nothing but the joint PDF. Okay, so this is the case. Actually, you can see here, suppose you have a continuous time signal, your xi will be in this form, and you have a constant. Suppose you have a constant, let's say this constant is a, and over the constant, what you are seeing here, you have a constant a, and a noise is added above it, and this noise is having 0 mean. For example, if it is 0 mean, then its unit variance if it is having unit variance, and if it is having, sorry, not unit variance, if it's having a variance of sigma x square, and it is having a mean also, and if the mean is mu x, okay, this mean can be 0 also. So it is having a mean and a variance. It is having a mean and a variance in general. Okay, so if it is having a 0 mean, suppose, then the signal will be looking like this. This is your random process. Okay, so this is because here actually this is the noise part having 0 mean and variance sigma x square. Okay, so this is the case actually if mu x is equal to, if the noise is having a variance which is equal to 0, sorry, mean is equal to 0. Now what will be the, in this case, I have already told you that this is your random process. In this case, what will be the expected value of xi? The expected value of xi is nothing but expected value of a plus expected value of wi. But you know that expected a is a constant, so it is a plus expected value of wi. Suppose wi, usually it is a 0 mean noise, then it will be equal to 0. Then expected value of xi will be equal to a. Okay, this is your mu x. So mu x will be a basically in this problem. Now what I want to tell you is that because this is very important notion that we will see later in estimation theory. Okay, so please note this thing. And next actually we will discuss some important concepts on the mean of a random process. Okay, so mean of a random process. So we have a random process x of t, then the expected value of x of t is nothing but the mean of the random process. We usually represent it as mu x of t, and this is equal to integral minus infinity to infinity x into fx of t into x dx. Okay, so this is what the mean of the random process. And what about the variance of the random process? The variance of the random process x of t is nothing but expected value of x of t minus mu x of t, and we have to square it and average. Averaging means expectation. So this is nothing but x minus, okay, in general you can say x of t also, x minus mu x of t the whole square. You have to integrate from minus infinity to infinity f x of t of x into dx. Okay, so this is how you can find the variance of the random process. So the formulas are almost the same. Okay, so this is nothing but the variance of x of t. So next we will talk about an important concept, that means it is known as the autocorrelation function. So autocorrelation function, autocorrelation function. So the autocorrelation means it's the correlation of a signal with itself. Basically the autocorrelation means is the correlation of a signal with itself. Okay, so what is it? Suppose you have a random process which is something like this, and you observe at time t equal to t1, and let's say this is time t equal to t2, and at this time the value of the random variable is x of t1, and at this time the value of the random variable, this is x of t2, and the time difference between these two time instants is nothing but t2 minus t1, which is defined as tau. Okay, now the autocorrelation function usually represented as ACF, autocorrelation function, is defined as the expected value of x of t1 multiplied with x of t2. Okay, so x of t1 you are multiplying with x of t2. Suppose you see here, if x of t1 is a large value, if x of t1 is a large value, is a big number, and x of t2 is a large value, suppose you are considering two time instances, something very close, then the chance that if this is tau is very small, okay, it's very small, you can say, if tau is very small, then the probability that this value and this value, both values, that means x1 and x2, both are higher, is very high, right? But if we have a case, if t1 is here and t2 is here, then if something like this, if t1 is here and t2 is here, the time difference is large. See, if the time difference is large, the chance that the product become, if you multiply two numbers which are very large, then the product, the result also will be very large. If one of the number is small, then the result will be very small. So that is the idea. So if you are just multiplying two numbers, here x1 and this is x2, but you see here x1 and x2, actually one of the number is very small, then the chance that the probability that both are having the product is a large number is actually very less. So the notion of correlation, actually we are considering two time instances, let's say this is t1 and this is t2, and we actually look at the random process and we will multiply the x of t1 with x of t2, and we will average it over all possible values. Okay, now this is nothing but the autocorrelation function. So the autocorrelation function, mathematically it can be defined as x of t1 with x of t2. Okay, so actually it is giving an amount of correlation between time instances. You see here, if the time instances are very close here, in this case it is very close, if these instances are very close, the probability that both are high is very high, right? So the correlation is strong. So the correlation is high. But you see here, this is a large number and this is a small number, and if you product these two numbers, then the result also will be small. So the probability that the result become high is very low, so it is less correlated. we can say, less correlated. So this is the idea. So we can represent this as, since we have two time instances and we have the random variable x1 and this is the random variable x2, x1 takes the value small x1 and x2 takes the value small x2, then this can be written as, we have to integrate over all possible values of x1 and x2. That means we are taking the product. That's why x1 and x2, fx of t1, fx of t2. Then we will find we have the joint distribute density function, then dx1 dx2. Okay, so this is nothing but the autocorrelation function of a random variable. Okay, now we will see this is expected value. So the autocorrelation function is nothing but expected value of t1 multiplied with expected value of t2. If t1 is equal to t2, then we know that it become x of t1 into x of t2. That means t1 equal to t2. So I will replace t2 with t1. This is nothing but x square of t1. Okay. So this is giving you what? You see here it is expected value. Expected means it is the average. And the square is actually denoting the power of the signal. So what is it? Average plus power. That means it is nothing but it is giving average power of the signal. This is giving the average power at time t is equal to t1. Okay. And this is giving, so autocorrelation function. So if t1 equal to t2, if t1 is equal to t2, that means that you are observing at the same time. So you have a t1 and suppose this is t2 and this difference is t2 minus t1. But if t1 equal to t2, then it means that your time difference is 0, right? So if we are observing at the same time instance, you can see here that it is giving you the average power of the signal. So you can also represent this as expected value of t1, expected value of, in general you can say expected value of t, you observe at another time which is nothing but t plus tau. Or you can represent, you can have another thing in this way also. You have expected value of t and t minus tau. Okay, that means you have a time difference. What is the time difference here? The time difference is equal to tau, and here also the time difference is nothing but tau. Here also the time difference is tau. So this is nothing but the autocorrelation function. So all these are representing autocorrelation function of a random process. Okay, so now we will see another important characteristics of the random process, which is nothing but the autocovariance. Autocovariance. So this is autocovariance function. Okay, autocovariance is usually denoted as Cx of t1 and t2. Is almost the same like your autocorrelation function. It is nothing but x of t1. The autocorrelation function, you have two things, x of t1 and x of t2. Okay, but here you are talking about the covariance. So you have to subtract the mean of the t1, mu x of t1. Okay, and you have to subtract the mu x of t2 from this. Then only you will be getting the variance. That's it. Okay, this is known as the autocovariance. So this can be also written as, okay, the expected value of x of t1. You just multiply this thing with here, and sorry, this can be multiplied here. So x of t1 into x of t2. Okay, then minus, if you multiply this term with the second term, minus x of t1 into mu x of t2. Okay, okay, then you take the second term and multiply here, minus mu x of t1 into x of t2. Then you take this term and multiply here. So minus of minus become plus, minus into minus become plus. So mu x of t1 into mu x of t2. Okay. So this is nothing but expected value of x of t1 into x of t2. So you have already seen what is this expected value of x of t1 and x of t2. This is nothing but the autocorrelation function. So we have another notation for this. We have the notation that it is Rx of t1 and t2, or it is having another notation Rx of t and t plus tau. Both are same. Okay. So you can have Rx of having a notation Rx of t and t plus tau. Okay. So this is nothing but your autocorrelation function, which is Rx of t1 and t2. Okay, since here it is represented like this. Now minus, if you take the expectation, then what will happen? Mu x is a constant, this is a constant. So minus mu x of t2, that is a constant. Then expected value of x of t1 is nothing but mu x of t1. So this become mu x of t1, okay, minus, this is a constant again, because mean mu x of t1, and this become, if you take the expectation of this become mu x of t2, okay. Then plus, you see here expected value, if you apply the expected value of this, then this become, it's a constant, so mu x of t1 into mu x of t2. Now you see here we have many terms. Out of that, this is a positive term and this negative term, both will cancel. So what is the final answer? The final answer will contain only this one and this one. So the autocovariance Cx of t1 and t2 can be represented as Rx of t1 t2 minus the mu x of t1 multiplied with mu x of t2. Okay, so that's it. So this is how to find the autocovariance. Now what is the variance? I have already explained. The mean square value is also explained. So I hope all these things are very clear to you. Okay. Now we will see an example. Okay. We have a x of t which is given as a cosine of 2 pi into t, okay, where it is given that a is a random variable. Then we can find the expected value of x of t, as the expected value of a into cosine of 2 pi t. But you know that this part is not a random variable. So this is nothing but, expected value of a into cosine of 2 pi t. If something is not a random variable, you can take it outside. Okay. So that's it. Now we can, so this is the mean of this random variable. Okay. Now we will random process. Now we will find the autocorrelation function. How to find the autocorrelation function? It is Rx of t1 and t2, which is nothing but the expected value of a into cosine Rx of, it's nothing but expected value of x of t1 into x of t2. Okay. So this is nothing but expected value of a into cosine of 2 pi into t1, then a into cosine of 2 pi into t2. That means you just substitute t1 and t2. Okay. Now this become expected value of a square into cosine of 2 pi t1, because I can take these two things outside. So cosine of t1 into cosine of t2. So cosine of 2 pi into t2. Okay. So this is nothing but the autocorrelation function of this random process. I hope this is clear to you. Now what is this expected value of a square? What is this? expected value of a square. It is the expected value of a square into cosine of 2 pi into t1. So cosine of 2 pi into t2. 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 So cosine of 2 nothing but the mean square value of A. It is nothing but the mean square value of A. Now we will see an important observation from here. At time T1 is equal to T2, then Rx of T1 and T1 is nothing but expected value of A square into cosine of 2 pi T1 into cosine of 2 pi T2. So this is nothing but expected value of A square into cosine square of 2 pi into T1, or in general you can say that this is nothing but the average power. This is nothing but the average power of this signal. Okay, that's it. Now we will see what is the autocovariance function. Okay, that means it's Tx of T1 and T2. Okay, and this is nothing but Rx of T1. We have seen the formula, Rx of T1 T2 minus mu x of T1 into mu x of T2. So this is nothing but we have this sorry, not this one. We have the Rx has this formula. So expected value of A square into cosine of 2 pi into T1 cosine of 2 pi into T2. Okay, this is the first part, minus mu x of T1. That means we have seen what is the average. The average is nothing but expected value of A into cosine of 2 pi. So expected value of A into cosine of 2 pi at T1. So T1. So this is this part, and the second part is expected value of A into cosine of 2 pi into T2. So this will nothing but, you can see here there is an expected value of A here, expected value of A here. So this become expected value of A square here, this one, minus, you can see a product is here, and also this one and this also constitute a product. So we can take expected value of A, which is expected value of A into expected value of A is expected value of A the whole square. So like this. So expected value of A square minus expected value of A the whole square multiplied with cosine of 2 pi of T1 into cosine of 2 pi into T2. So this is nothing but your covariance. Okay, but what is this? This is nothing but the variance of A. Am I correct? So this part is actually showing, this part is showing the variance of A. So if you know the variance of A, if you multiplied with the cosine of 2 pi T1 into cosine of T2, then you are getting actually the auto covariance. Okay, I hope this part is very clear to you, right?